pretty much every second year chemistry course or AP chemistry course does some iteration of identifying a metal carbonate lab activity. So I want to briefly go over kind of the overview and the procedure for this lab. I'll show you some sample data, and then I'll talk about the pre-lab calculations just a little bit as well. In our lab, we're going to be using alkali metal carbonates, and there are three possibilities for the one that you will use: lithium carbonate, sodium carbonate, or potassium carbonate. All three of those react in a very similar way. So in my chemical equation here, I'm just going to let X take the place of one of those metals. So X is our alkali metal, or our group 1 metal. We're going to react that compound, and these will be kind of white, powdery compounds. We're going to react that with an acid, and specifically in our lab, we're going to be using hydrochloric acid. Any other acid would work, though, but HCl will be the one that we're using. And the most distinguishing product that we're going to get out of this chemical reaction is the carbon dioxide. So the reaction mixture is going to bubble and fizz when we mix our acid into our solid carbonate. That'll be the carbon dioxide that's being released. It's going to be produced as a gas because we're at room temperature. This is a very similar reaction to baking soda and vinegar. So baking soda is a hydrogen carbonate, vinegar is acetic acid, bubbles and fizzes makes CO2. In addition to that, we're going to make water, H2O, as well as an ionic compound. That's the alkali metal with the chloride anion from our hydrochloric acid. The first set of calculations that you do out of this lab is just going to be a mass difference calculation. So we know that law of conservation of mass tells us that the mass of the reactants in a chemical reaction will be equal to the mass of the products in the chemical reaction, right? Mass is not created or destroyed. But in this specific case, since we're producing a gaseous product, this carbon dioxide, if we do mass of the reactants minus mass of the products, the difference there is going to be the carbon dioxide that's lost through the reaction, right? That carbon dioxide is lost as a gas, which means it's going to bubble up out of the solution, come out of our flask, and we're not going to capture it and be able to measure its mass. And the way that we're going to identify which alkali metal carbonate that we're using in this lab is by doing a mass ratio. Specifically, we're going to look at the mass of the carbon dioxide that's produced in the reaction that we get from doing our mass difference. And we're going to do a ratio of that to the mass of the compound used in that trial. And so the idea there is that since mass is conserved in a chemical reaction, the ratio between the carbon dioxide produced will stay the same as the ratio to the carbonate in the original compound before it reacted. So here are some sample student data, and I kind of just want to show how we're going to get this mass ratio using some actual data here, actual numbers. So you can see the students done 3 trials, and for each trial they have calculated the mass of CO2 produced in that trial. So again, by doing the mass difference between the reactants and the products. And then along the way, they also have calculated the mass of unknown compound that they've used. So that's the alkali metal carbonate that they started with at the beginning of before the reaction. Okay, so the mass ratio that they're doing here to get this 40% is the mass of the CO2, so 1.034 grams, to the mass of the carbonate, 2.572 grams. And then to turn that into a percentage times 100. And so that comes out, they've rounded this to 4 sig figs, of course. So that comes out to 40.20%, which is what we see up here. Now, in order to make sure that we get 3 really good trials in this lab, we're going to use something called deviation from the mean. And this is not something that we will typically do in our labs this year. So I just want to take a couple minutes and just sort of explain that process and sort of what we're looking at. So you can see in the far right column, the student has deviation from the mean for each trial. So the way that we calculate the deviation from the mean is you're going to calculate the mass percent of CO2 for each of your 3 trials. So there they are. You're going to get the average for those 3 trials. And so for these data here, that average is 40.57%. So the deviation from the mean is we're going to compare each trial to the average. So for example, in trial 1, we're going to do our average, 40.57, minus the mass percent for trial 1, 40.20, and so the deviation from the mean there is 0.37%. So we want 3 trials that are really, really close to each other. And so when we calculate deviation from the mean, that's going to allow us to really pinpoint any trials that stick out. So for example, for this student's data, you can see that they have 2 trials that are 0.37% off of the mean, and then 1 trial that's 0.73% off of the mean. So I think trial 2 is just a little too far away compared to the other 2 trials. We're going to go for 3 trials that are within 0.01% of each other, right? So we want them to be really, really close. So in this case, we would go back and we would do another trial to replace trial 2. And that's going to ensure that we get some really good data so that we can do our analysis. All right, lastly, I want to go through an example calculation that's really similar to some of the calculations you'll be doing for the pre-lab. This is a pretty simple calculation, but I know that it's been a little while since we've done stoichiometry stuff, especially if you're a 12th grader this year. Maybe it's been a lot longer than you realize. So I just want to kind of talk through this process, and hopefully that way you'll be a little bit better prepared for the pre-lab. Okay, so we have our balanced chemical equation here. This is rubidium carbonate reacting with hydrochloric acid to make carbon dioxide water, and then rubidium chloride. So again, really similar to the chemical equations that you'll be looking at for this lab. And we want to calculate the minimum volume of 6 molar HCl needed to react completely with 5 grams of rubidium carbonate. So how in the world are we going to do that? Well, the first thing that we've got to do is we've got to take this 5 grams of rubidium carbonate and we got to turn that into moles. And so the way we're going to do that is we're going to divide 5 grams by the molar mass of rubidium carbonate. Okay, so there's my first step. So we're doing 5 grams of our compound divided by the molar mass of that compound. So I just went and I added up the molar mass of rubidium carbonate using periodic table. Actually, I didn't. I just Googled it, but that's how you would get the molar mass. Okay, and since we're going to HCl, the next step here is we're going to use the mole ratio from our chemical equation. So our chemical equation tells us that we have 2 HCl for every 1 rubidium carbonate, right? I didn't write my coefficient of 1 over there, but we know that that's just a 1. So 2 HCl to 1 rubidium carbonate. All right, so I pop that in the calculator and I get my moles of HCl. So my next step is I need to figure out what volume of HCl we need. And I'm going to show you two ways to do this. I'll show you kind of the dimensional analysis way so that it fits in line with everything that I've got here. And then I'll show you another way that might be a little bit easier to wrap your head around. Okay, so we have 6 molar HCl, which means that 1 liter of HCl contains 6 moles. So molar, or that big M, is moles over liters. And so I'm just going to flip that over so that my units cancel out there. And that'll get me liters of HCl. Okay, so you can use that as a conversion factor in line with everything. A little bit of a longer way to get to that same answer that might make more sense, though, is by using our little triangle down here. So again, all of this comes out of the molarity equation, which is moles over liters. We're going to use that so much this year. So using this triangle down here might make a little bit more sense. So in this particular calculation, we want to solve for volume, or we want to solve for liters there. So what I'm going to do is I'm going to cover that up in my triangle. And so the way that I'll solve for liters is I'll do my number of moles divided by the concentration. And so I have calculated my moles here, and I was given the concentration in my problem. So I'm just going to do that number of moles divided by the concentration. All right, so there we go, 0.0072 liters. I went ahead and rounded for 2 sig figs. And then we could put that in milliliters to make it make a little bit more sense. All right, there we go. 7.2 milliliters would be the minimum volume that we need there. So you'll notice in our lab procedure that we're going to be using volumes of acid way beyond the minimums that you calculate in the pre-lab. And that's because we want to make sure that there's a complete reaction. We want to ensure that the carbonate that we're using is the limiting reactant. So we're going to add a lot of HCl just to make sure that we react it completely and get out all that CO2 so that we get some good data. All right, hope that was helpful. Thanks for watching, and I'll see you soon.